We will start by fundamentally changing how you view a matrix. We typically learn matrices as grids of numbers to be memorized and multiplied. Instead, imagine the 2D coordinate plane as an infinite sheet of infinitely stretchy rubber. The columns of the matrix tell you exactly where the fundamental grid lines, the x-axis and y-axis, land after the transformation. If you place an object on that fabric, the matrix transforms it too. A matrix is simply a set of instructions for how to stretch, squish, shear, or rotate that entire fabric. Each column tells you where the basis vectors land. Now watch as we apply this matrix, the entire plane shears and stretches. The rubber sheet deforms, carrying everything on it to new positions. Notice, the first column 2, 0 is exactly where I hat landed. The second column 1, 1.5 is exactly where j hat landed. The columns are the destinations of your basis vectors. A matrix doesn't just hold numbers, it reshapes the world. Let's now populate our space with vectors, arrows with length and direction, and explore how transformations change them. Here are 3 vectors, each an arrow with its own length and direction, living on our 2D plane. Remember projections from the dot product. The projection of B onto A is like shining a light and catching B's shadow along A. It tells us how much of B points in A's direction. Now the key question. When the matrix acts on the space, every single arrow moves to a new location. How do these shadows change? Let's start with a pure 90-degree rotation. This matrix rotates every vector counterclockwise by 90 degrees. Watch, every arrow rotates together. The lengths stay the same, the angles between vectors stay the same. A rotation preserves the geometry, it just spins the whole world. Notice, the projection, the shadow of B onto A, has the exact same length as before. Rotations preserve dot products and projections. Now let's try something different, stretching everything horizontally by a factor of 2. The x-coordinates double while y stays the same. Watch the arrows now. The horizontal components double, but the vertical components stay put. This changes the lengths of the vectors, and critically, it changes the angles between them. Look at the projection now. The shadow of B onto A has a completely different length. Unlike rotation, a stretch distorts the relationships between vectors. Dot products and projections are not preserved. The key insight: rotations preserve the geometry of your vectors. Stretches reshape it. Understanding which transformations preserve what is at the heart of linear algebra. Let's open the hood and see the actual math behind rotations and stretches. We'll work through the calculations step by step. A rotation matrix has a beautiful structure. For an angle theta, the first column, cosine theta, sine theta, tells us where the unit vector I hat lands. The second column, negative sine theta, cosine theta, tells us where j hat lands. Let's calculate. Take the vector 3, 1 and rotate it by 90 degrees. Cosine of 90 is 0, sine of 90 is 1. So our rotation matrix becomes 0, negative 1, 1, 0. Multiply the matrix by our vector. 0 times 3 plus negative 1 times 1 gives negative 1. 1 times 3 plus 0 times 1 gives 3. The result is negative 1, 3. Watch the geometry. The vector swings exactly 90 degrees counterclockwise. Its length stays the same, only its direction changes. That is the hallmark of a rotation. We can verify. The original length is square root of 3 squared plus 1 squared, which is root 10. The rotated vector, square root of negative 1 squared plus 3 squared, also root 10. Identical. Now let's look at a horizontal stretch. The matrix has k on the top left and 1 on the bottom right. This scales every x coordinate by k while leaving y unchanged. Let's stretch the vector 2 horizontally by a factor of 2. 2 times 2 plus 0 times 2 gives 4. 0 times 2 plus 1 times 2 gives 2. The x component doubled from 2 to 4, while y stayed at 2. Geometrically, the arrow gets pulled to the right. The x component stretches from 2 to 4, but y stays at 2. This changes both the length and direction of the vector. The length jumps from root 8, about 2.83, up to root 20, about 4.47, and the angle with the x-axis drops from 45 degrees down to about 26.6 degrees. Stretches warp everything. Let's put numbers to it. Take vectors A equals 21 and B equals 12. Their dot product is 2 times 1 plus 1 times 2, which equals 4. The angle between them is about 36.9 degrees. After a horizontal stretch by 2, A becomes 41 and B becomes 22. The dot product jumps to 10, and the angle between them shrinks to about 31 degrees. The stretch has squeezed them closer together. To summarize, rotation preserves everything: lengths, angles, and dot products. Its determinant is always 1. A stretch changes all of these. Its determinant equals the scaling factor k. Understanding what each transformation preserves is the key to mastering linear algebra. Here is the major cognitive jump. We are about to discover eigenvectors. Imagine the plane filled with arrows radiating from the origin in every possible direction, like a dandelion. Each dashed line marks the original direction of its arrow. When we apply a transformation like shearing the fabric, most arrows get knocked off their original line. They change both length and direction. But look closely. A rare, special set of arrows survived. During the stretching and squishing, these arrows stayed perfectly on their original line. They never tilted away. Let's replay the transformation, watching only these survivors. As the grid warps, they slide perfectly along their own lines. This arrow, along the x-axis, stretches out to become exactly twice as long. Its eigenvalue is lambda equals 2. And this diagonal arrow shrinks to half its length and flips completely backward, still on its line. Its eigenvalue is lambda equals negative 0.5. The negative sign means it reversed. They might get longer, shorter, or flip backward, but their direction is immune to the transformation's rotational effects. These structurally vital arrows are the eigenvectors, from the German eigen, meaning own or characteristic. The amount they stretch or shrink is their eigenvalue. This is captured by the fundamental equation: A times v equals lambda times v.